are going to look at what happens when we move letters from box to box. So we want to consider these three boxes. We draw a letter from box 1 and we place it in box 2. So what this is saying is we're going to draw a letter from here. Say we draw a B. We're going to put that B inside here. And then we're going to draw randomly a letter from here, and we're going to put it in here. And then we're going to draw a letter from box 3. And we want to know what that letter is. Okay. So how do we look at this probability? Well, the best way to do this is definitely a tree diagram. Because you have either, on the first box, you have either an A or B. Here, you start out with 2 out of 3 and a 1 out of 3. Okay? Then, let's talk about what happens if you do an A or a B. If we do an A, you now have this. So if we put an A in there, we now have 3 letters, and we have 2 A's and 1 B in box 2. If we drew the B, it would look like this, and so we can still draw an A or a B, and therefore it would be 1/3 and 2/3. So it depends on, did we draw the B or did we draw the A? Now, again, I'm going to go up above this time. It's going to depend on, did we draw the A? If we draw an A, we're going to look like this. If we drew a B, we're going to look like this. And it doesn't matter which box it came out of, it's just an A or a B. So if we drew an A, we get 2 out of 5. So that's 2/5. If we drew a B, and that would be 3/5. And that's no matter which A we drew. That would be 2/5 and a 3/5. If we drew a B, let me erase that because that should be an A. If we drew a B, it would be a 1 out of 5 and a 4 out of 5. A 1 out of 5 and a 4 out of 5. So if we follow our branches, so we want to know what is the probability that the letter drawn from box 3 is a B. So we want to know these 4 branches. So we have a 2/3 times 2/3 times 3/5. Then we have a 2/3 times 1/3 times a 4/3. Nope, sorry, that's 4/5. Let me change that. That's 4/5. Then down here, we have 1/3 times 1/3 times 3/5. For down here, we have 1/3 times 2/3 times 4/5. So when we multiply across, we're going to get 12/45. We will get 8/45, 3/45, and 8/45. And we're going to add these up because I can get a b this way, or this way, or this way, or this way. So I'm going to add these up, and that will get me 31/45. So here, you can't just go, there's a total of 3, there's a total of 2, there's a total of 4. You have to realize that you are drawing from box 2 and placing it in box 3. So you're going to have an additional value in each box. So your denominator is actually going to increase from 2 to 3 or from 4 to 5 in those boxes. And your numerator is going to change based on what you drew in the first selection. And so this particular one is going to be a little bit different based on what you drew. Now, because the sample space and everything changes based on what you drew from the first one, this is considered conditional probability. We know something about the space. When the experiment is affected by additional information, the new sample space is reduced in size usually, but we also know something. Now, if you think about conditional probability, remember earlier when we said without replacement. This is definitely going to be a conditional probability because we know something about our sample space. We know we took something out of our sample space. So if we talk about, like here, rolling a 5 on the die, well, that's just 1 out of 6, right? Probability of getting a 5 is just 1 out of 6. What's the probability of rolling a 5 given that it is an odd number? We know that it's an odd number. So probability of 5 given, this line right here is going to represent given that it's an odd number. And so we know that it's 5. There's one of them. But if we think about the odd numbers, there's 1, 2, 3 odd numbers. So now I only have a 1/3 chance because I know something about my sample space. It can only be one of these 3 possibilities now. So I have reduced my sample space in order to give myself some type of condition.